Okay, chapter 4 relates the input-output relations. So our input-output relation is really excitation and response relation. All the mathematical relation is really shown in chapter 4, but beforehand, up to chapter 3, give you the basic probability theory, which can be used really for the chapter 4 and chapter 5 and so on. Without that knowledge, you can't handle the single input, even single output relations. So then this chapter 4 is how we're going to handle that. And this relates not only theoretical aspect, we are talking about application into the testing. Without this knowledge, I can say you cannot, or hard to apply and use for testing. When you put the transducer, the reason is you put the transducer to get the measured output or measured input, then you can manipulate to get the result in time domain and the frequency domain. So that's kind of important. And here, this is like any testing system. Any testing, simplest could be, which I always use in the past, is a simple plate. It's suspended by the two bungee cord, that's like a rubber, a thick rubber string. And just wrap around here, and wrap around here, and put the shaker right here. Small, not fixed on the base, a small self-stand shaker. Then just attach a screw in to the plate. So it's a shaker. I can say, then you shake it. Then there is a transducer, as I showed the other day, mounted right on the center of the shaker. Then it shakes it by itself. Then generate the input, excitation as a force or acceleration or velocity. Sometimes use a force gauge, or sometimes use accelerometer right there. Then you can convert into the velocity if you want, and so on. And input excitation right here. And this is output transducer. Typical one is a Kazuki, accelerometer. Kazuki is a very typical one. And you can say X and Y. All the measurement is done in time domain, in time. So this whole thing is a system. So a plate is like the simplest system. And depend on the size, there's a system parameter, small h and capital H, could be different, okay? So if this is a whole building, for example, whole ship, whatever, then the point you excite is like xt, and this is a yt, and you can generate this parameter, this function, which is really like a transfer function. If you took a control course, then they talk a lot about the transfer function. The vibration shock area, you talk about the frequency response function, which is identical. No difference. Simply y over x. That's what that is, okay? So it's fully understandable. Then sometimes you know the input, you know the output by the measurement, then you can determine the transfer function in frequency domain or the impulse response function in time domain. Okay? Sometimes you know this, and then you know the xt, then you can determine the y response in frequency domain and the time domain. So this is a system parameter or system functions. And in chapter 2, I believe, or chapter 1, we talk about the constant parameter linear system. Here, we are not dealing with a nonlinear system. Okay, so this is a small oscillation problem. Input-output is usually here is a linear elastic system. Okay, linear elastic. That's what we are dealing with. And for the nonlinear stuff, of course, that's the next step to handle. And here is, I said, we're going to assume, or saying X is algorithmic process. Okay, which means what? Because this is a constant parameter linear system. What does it mean, constant parameter? I talk about that. What it means, constant parameter linear system. Like mx double dot plus cx dot plus kx is equal to force, that m, c, k are the constant. It's assuming it's not the time varying parameter. Okay? So for the time varying parameter, that's a nonlinear system. It changes as time elapses. So h, t, comma, tau, this is time delayed, is a tau. T is arbitrarily that's just a time parameter. And t is minus infinity to infinity, whole domain, but we'll simplify because we are living in the somewhat ideal world. Okay, the ideal system of relations. If I ask you, don't look at your note, write it down, the convolution integral, sometimes not easy. You will screw up easily t and tau. So that's why I said it's a good idea to write it down by looking, write it down, then to hear is the best. Look at this. This is really convolution integral. We talk the Wednesday. H, this is a response. Yt is a response. Yt is from 0 to infinity. Theoretically infinity. Reality is a finite time, okay? And h tau xt minus tau d tau, the h here is a real function. If tau becomes 0 and goes negative, doesn't mean anything. Impulse response function. When the response starts, at the time you apply the forces, then it starts. So tau has to be physically realizable, that has to be 0 or greater than 0. So when tau is equal to 0, then tau is less than 0, meaningless. So always the range of tau is 0 to infinity. Okay? But mathematically, the expression could be minus infinity to infinity. Physically, what that means is in chapter 4 of my vibration lecture note. I gave you chapter just 4, impulse, and I told you read, very easy to read that. My lecture note is always thin, but a lot of stories are in there. What do you call this H tau? What did I say? What did I say? Unit impulse response function. Physically, what that means is this. You have some excitation. It's like xt. Excitation, x could be force, okay? Then in numerical, to get the numerical solution, how do you do is you slice this guy with a strip, with all these strips. Okay? So I'm going to just pull out the one strip here. One strip, just let's say that strip could be like this, which is impulse. Simply, I don't know whether you saw the modal hammer or not. You might have a chance to see that. Then at the tip, it has a force transducer. Bang onto it, on the plate or whatever, bang onto it. Then what the response would be? Response would be this kind of the response, right? When you apply the impulse, then this is the response. This is the response, the yt. Okay, yt is equal to, as indicated there, is t h tau x t minus tau d tau. So this y is after applying the impulse. Then this is the measured output. That's what this is. Measured output is like this. This is unit impulse response function. And this is, for the given system, this is a fixed parameter, fixed function. Of course, this excitation is keep changing. As you change the plate much longer and wider, then of course impulse response function is changing. Anyway, so if you look at chapter 4 for vibration note, with the no viscous damping situation, impulse response function, or called unit impulse response function, is purely sinusoidal. What does it mean? Why sinusoidal? I wrote here it's a decaying, but I said there that's a sinusoidal. For the sinusoidal, if it's a sinusoidal, what happened? You have frequencies about the same, but there is no decay. It's like this. Why? It's constant sine vibration because no viscous damping in the system, which is simply mass and spring system. If you have the damping in single degree of a freedom system, M, K, and C, then of course it decays, right? For the measure of the decay due to the viscous damping, we use the zeta. This zeta is some people call the critical damping ratio. It's in all beginning of the vibration. If you forgot, then read very thin chapter 4 of my lecture note. And if you replace omega n here by omega n times square root of 1 minus zeta square, then you will get that for the damping case. In addition, you have to add this term. This term is envelope of the decay. Okay? For the no damping situation, of course, this zeta is equal to 0, which means this term is 1. Otherwise, envelope of the decay is what this term is, okay? So H functions are fixed for the given system. So, well, of course, this is a function of the time t. And if you look at here, there is no t. There is no tau. What happened? What happened here? I typed this up and generate this note really some years ago, but still made a mistake. What? Find the mistake. What is it? T and tau. This tau should be the t. Okay. That should. See, this is blind for many years. What happened? That sometimes who discover? Most of the time, students you discover. Well, that's what we are. Nobody is perfect, right? So you look at it. Especially KAIST students is pretty bright students. Yeah. So next is like let's say stationary input, and also a lot of time the algorithm input. But the direction I'm heading, I want to first walk through. I'm trying to formulate the output using the input. Okay? So this Y is output. Y is output. Now this is what? X is input, right? So then determine the expression for Y. I'll come back. What's the Y? The output. Then RY, we learned that. Then RXX, RYY. X portion is excitation input portion. Y is output response portion. So what I'm doing here is get the expression of output using the input excitation with the system parameter, which is like small h. Okay. So that's what I'm heading for. So that's what this is, just the first. Then express RYY using RXX as input, the autocorrelation function, and also H is the system parameter, unit excitation, unit impulse response function. That's the system parameters. Okay? That's what we are dealing up to chapter 3 is autocorrelation function for X only, then Y only. then we determine Rxy expression, cross correlation function. Then you can take the Fourier transform of correlation function to get what? To get spectral function. Spectral function. Then we looking into the correlation coefficient, the covariance, all different functions. We look at it. Then you can apply it. That's the idea. So here is RYY. We'll come back. Then RXY. Okay. If you take the Fourier transform of Rxy, what do you get? Spectral cross spectral density function. So vice versa here. So this is what we are heading. By looking at this one at a time, so let X and Y are the algebraic processes. What does it mean X and Y are algebraic processes? Algebraic process. One time history represent the ensemble of sample functions, right? So rather than dealing the whole ensemble, then you can deal only the one sample frequency, which represent all the statistical property for ensemble property. And take a look at a little bit here. If you look at the Y, using the expression shown right up here, right here. Just remember this for a while. Y is integration of h, in fact this is a tau, x t minus tau. This is one expression, but over here this is a 2. The output expression y t multiplied by y t plus tau to get what? To get RYY. RYY is equal to the expected value of y and y t plus tau. So you have to have a multiplication of y t plus y t plus tau. Okay? And by the way, this is expressed like h comes first, as it shows here, but you did exercise already for this convolution integral we did the day before yesterday, and h tau x t minus tau d tau, right? And this is equivalent to the x t minus tau h. I'm sorry. See, if you don't pay attention, x tau, may think, h t minus tau d tau. Sometime in the past lecture, the first week lecture, vice versa, I said derive this. This is all the same. Or if you look at it again, this is all belong to vibration. So chapter 4, first page of your lecture note, then you see that I prove this is equivalent by let this guy is equal to T1 and replace this And in general, this is like this. If in reality, it starts from 0 because it's a physically realizable system. So if you look at there, make sure you should be able to derive the relation, the equivalency of this expression. A lot of things I have done, then after for a while, if I use that equivalency, then sometimes I don't remember, sometimes you don't remember. For example, as a reminder, I'm gonna something like this, and I forgot. Sometimes this minus tau. Let's say this is equal to ryx or something like that. Question. We proved this some time ago. Then you don't remember this, but you should be able to prove it right that moment. So that's what I demand. For example, we'll face this next week, okay? So that kind of the things is what. So chapter 4, don't memorize it, but understand the first physics part of it. So here, by looking up that, first expression is a double integration because it's a 2 output with the time delay tau. So ht relate with h theta 1 times x t minus theta 1, because this is theta. Think about this, theta 1, theta 2 are the integration parameters, and theta 1 is like a tau up there. Tau, t minus tau, okay, expression. And if you look at yt plus tau, yt plus tau is again over here. The h theta 2 is like h tau. Then t plus tau, this is what t plus tau is coming right from here. And there should have a delay, another delay, minus theta 2. And double integrations, okay, for theta 1 and theta 2. So it's a little bit messy. So, but that's very clear, okay? So integration first by theta 1, then by the theta 2, second time. And now you take expected value of this y and yt plus tau. Expected value, by definition, is what the ryy is, right? You agree, right? Because we have done this, all the elements, we got all the engine parts. Engine parts. How many parts the one engine passenger car has it? I forgot. How many motors the naval ship has it? That I remember. Like 600 motors. The Boeing 747, how many fastener, which means bolt, screws and all that, how many are there to build the 747? As I recall, how many you think? Guess. 100,000? Fastener, bolt, screws, all bunch of fastener. Guess. That's too many. As I recall, it's about 2.5 million. A lot. So here up to chapter 3, we make all the necessary required the bolt. Chapter 4, from now on, we're going to put in a system to make an engine, to make the plane, and things like that. So now, the reasoning to do this is like RYY, RXY, SXX, SXY, SYY, whole bunch of different things. Then we proceed how we're going to use it. My interest is always not just the end as a formulation or expression for the mathematics. We are the engineer. We have to show how to use it. So sometimes it's very difficult to tell where to use it, but doing our best and all that. So the definition of this is an autocorrelation function of output response, YY. Now it has a output. Up to chapter 3, we don't have a name output. We are going to call the Y as output response. So it's output response, which is expected value of Y times Y t plus tau. Output response. Over the weekend, the stuff I cover here, do a little bit thinking, and if you have a time, write that down and all that. Once again, just to practice, then think. That would really help for next week's lecture. Output response, but as you look at here, it just carries over. This is expression, direct instantaneous multiplication of y and y t plus tau. Then now apply expected value. What does it mean, expected value? That's mean value. Mean value. What's the mean value? First moment. So here, expected value of this expression is right here. So here comes expected value of this guy. Then now, this h here and this h here is a system parameter, constant, okay? So then I can put it out, the outside of expected value. So I put the E applied, not here, take them outside of E. Here I have to still leave this inside the E. H, put it outside of E. Then Tx, t plus tau minus theta. Then apply for it. Same expression. This is equal to these two equations are identical when you apply the expected value. So next is this stuff is not tricky, nothing tricky, but very straight algebra. But you have to really know the path. Otherwise, you could easily screw up, but you will get back on the right track. So here is, so you have to start working on this portion. And t minus theta 1, t plus tau minus theta 2. Then I want to do a little bit manipulation. To be able to perform the integration. So let's look at this. T minus theta 1, I'm going to set that as a T1. Just rename it. So T minus theta 1, I'm renaming as a T1. Then here is a T here. T applies to here and applies to here. So I'm manipulating to make it simple. So T minus theta 1, I'm going to call that as a T1. Then if you rewrite this, T is equal to T1 plus theta 1, right? Then I'm going to rewrite this guy, T plus tau minus theta 2, as a T is a T1 plus a theta 1, just to carry this guy over. Then I'm going to just put the remaining term here, theta 1 plus tau minus theta 2, as put in the parenthesis. This portion is right here. Then replace into this. Put that in. This is a T1. So this you can express as a T1 plus tau theta 1 minus theta 2. Just to rewrite the expression such a way to get the result out. So over here, this is a final expression for autocorrelation function of response, y. Y is always response. It's a double convolution integral. Okay? And H is involved. Double convolution integral. It's autocorrelation functions. It's a little bit messier. Okay, so now to do Rxy is a single integral forms, not a double. Okay, this is a single integral form. X and x, by the definition of a convolution integral, x is here, and x itself is here, and xt plus tau is that portion. You feel something funny, isn't it? You feel something. I feel something funny. I feel something funny. Let me see. What? It's so funny. Oh yeah, you are right. Yeah. So old version. I think this is a somehow older version. So let's see. My node. You should be able to spot right away. That's good. So my node is y there. So my node is newer, corrected version, and this is old version. So that you have, Choro, you did the right thing. Watch, then when you see the wrong expression, you have to tell right away. Otherwise, it's gonna go. I can tell right away it's wrong. So this is a y. Chusong. This is a y. So because this y is from here to here. For the output, you have nothing else to do. X is x, right? For the y is integral of h times x. So this is what Choro spot right away. So this is this from here to all the way down here. And this is a t plus tau, and t plus tau, then minus the theta 1. Clear? Yeah. This is, I think I should replace the newer version. And this guy is also, I wrote the same thing over here. Yeah, this is a y, same thing. And this is Rxy. Then this is y. Okay? I'm developing Rxy. So first is x, second is y. So this should be the y t plus tau. But this is older version. Your note is a newer version. So your note is correct. Okay? Okay, Rxy. Right. And let's look at the next. So this is all the way same thing. Y. This should be a y. Then over here, this is x, and this should be a y. This is all the version which has the same mistake. So this is h. This is what? R x y. This is. I don't understand this. This is Rxy. This is this. This is something that. No. What's wrong here? Oh, this is wrong, right? This is this, because this is correct, right? And this guy, oh, this guy is wrong, right? This guy is not right. And next one, this is correct. You see, right? So this is correct because applied the h, right? This is okay. Then this is okay. So Rxy is equal to integral h Rxx. That's correct. Youngbin, okay? Yeah. And this becomes final. This is a final expression. I put that in a box. Rxy tau is equal to the h. This is Rxx. Check my corrected newer version is all okay. Yours are okay. This is bad. I'll replace it. Got it? Got it. I'll stop right here. And this is really expression for Rxx, Ryy, and Rxy. Rxx is same, autocorrelation function. That has nothing to do. We are dealing with, right now, we are dealing with the autocorrelation function Ryy. Then also Rxy, cross-correlation function of the output, expressed as a function of the input. Okay? So you may notice I really go through very slow because it's very easy to screw up. So that's what we do. And back to the midterm exam, and two of you try that. The problem number 2, problem number 5, all done because it's note. I made a mistake. I think Higgy wrote it down the right equation set, right? So do that. Any questions? Okay, Friday afternoon, you are free, right? So Friday afternoon, my lab, my students saying, "Oh, don't assign us anything. Friday afternoon, it's time to play." But no soccer game. Because, well, it's up to you. Okay, I'll see you Monday.